Okay, so previously we considered the total differential of a function. So let's say we have a function of three variables, f, that depends on x, y, and z. Okay, let's just call it u. We saw that the total differential, du, which is just df, okay, can interchange u or f, equals, okay, can you remember what it equals? It is df, partial derivative of f with respect to x, dx, plus the partial derivative of f with respect to y, dy, plus the partial derivative of f with respect to z, dz. Okay. Now, if you think about the dot product of two vectors, let's say we have a vector A with components ax, ay, and az, and a different vector B with components bx, by, and bz. What is their dot product equal to? It's ax times bx plus ay times by plus az times bz. Okay, so if you have a look at this and have a look at this, then you see there's some resemblance. And you see that we can identify a vector with components df by dx, df by dy, and df by dz, and a different vector with components dx, dy, and dz. Okay, and form this as the dot product of both. Okay, so this is the vector dr, which has components dx, dy, dz. And this is a different vector with components df by dx in the first x component. The y component is df by dy, and the z component is df by dz. Okay, and defining these two vectors allows you to write du as df by dx, df by dy, partial derivatives, df by dz, dotted with dx, dy, dz. Okay? And this thing pops up a lot, okay? And it's called the gradient of f. And we write it as this upside down triangle, the gradient of f. What is it? Is it a number or a vector or an elephant? Okay, it's a vector. Okay, it's got components. It's got x, y, and z components. And we're saying that df can be written as this vector dotted with this vector, dr. Okay, so this is called the gradient of f. So just let me go back a step. This is the gradient of f. Okay, sometimes just known as grad f. Okay, and this nabla, this is called nabla, this symbol. Okay, and this is a differential operator. So you can write this as d by dx, d by dy, d by dz, where it's understood that it will act on something. Okay, in this case it's acting on f. Okay, acts on whatever this something is, a dot. Okay, this is called the nabla operator, nabla. Okay, and you can write it in component form too, so either the gradient of f or this nabla, we can write it with unit vectors I, j, and k. So let's do that. Let's have nabla, it equals d by dx in the x direction, which has unit vector I, okay, plus d by dy in the unit vector for y, which is j, and d by dz in the unit vector in the direction of z, which is k, okay? And again, you're thinking that these act on something, okay? So we have that the gradient of f, which is a vector, it equals this thing, which we can write as df by dx in the x direction, df by dy in the y direction, plus df by dz in the z direction, okay? Okay, but I'm lazy with my vectors and I just use the round brackets with the commas. So this is the x component, the y component, the z component. Okay, so our total differential is just equal to the gradient of f, which is a vector, dotted with another vector. Okay. All right, so what does this mean? Okay, let me clean the board up and I'll explain a little bit more. Okay, so we call this the gradient of f, and we call this dr. So we saw that our total differential du or df, whatever you want to call it, is given by the gradient of f dot dr. Okay, one vector dotted with another vector. Okay, right. So what does this mean? What is this gradient? What's this vector represent? And what can we read into this total differential? Okay, so this is where the concept of a directional derivative comes in. So like I said before, you looked at derivatives, partial derivatives, df by dx, or df by dy, or df by dz, and this showed us what the change in the function along the curve described by the intersection of your surface and a plane at constant y, okay, for a function of two variables. So we had df by dx at constant y. Okay, so if we had a surface x, y, and z, so if we have a function of two variables, okay, this is given by a surface, okay, then we saw what the change in the function was. We saw that df by dx was the change in the function along as we change x for a fixed value of y. Okay, so we had a fixed value of y and we had a plane in the xz, and where this plane intersects the surface gave a curve. Okay, so we had a curve in xz that was the intersection of this xz plane at the value of y and the surface. Okay, and df by d, so z is a function of x and y. The derivative of this was given by df by dx. Okay, and it's understood that we keep y constant. So we've already seen the concept of directional derivatives, but only for two special directions. Along x, that's looking at df by dx, holding y constant, and along y, okay, this is holding df, this is df by dy holding x constant. Okay, so we have a yz graph now. And that's made from holding x constant, so we choose a value of x, and we draw a plane in the yz. This is a yz plane, and where that yz plane cuts the surface, you get this curve. Okay, and the derivative of this curve is df by dy at this value of x. Okay, so we choose a different value of x, then we choose a different plane. Okay, and we get a different curve. Okay, but this df by dy tells us the value of the derivative of this curve at any y. Okay, so we've got directional derivatives, but they're two special cases. They're along x and along y. But what if we want to know how the function changes in an arbitrary direction? Okay, so let's assume that this function z represents the height of a mountain. Okay, so the height of the mountain will depend on the x and y coordinates. Okay, and the mountain will be rugged. Okay, you may ask yourself, how does the height of the mountain change as I look? So you're standing on the mountain and you look around. Okay, how does the height of the mountain change? So how does this function change if I look in a certain direction? Okay, where is the steepest point of the mountain? Where is the flattest point? Okay, so you want more than just two directions. You want more. You want to be able to say more than just how does the height of the mountain change in the x or the y. Okay, as you move along x or y, you want to be able to walk in any direction you want and find how the height changes. Okay, so let's think about an arbitrary curve then. Okay, and let's say you move dr. Now before we saw that this dr was equal to a tangent vector t ds. Okay, this is the tangent vector from section 1. Okay, this means we can write df as equal to the gradient of f dot t ds. Okay, and ds is a number. Remember, it's just the magnitude of dr. Okay, so t is a unit vector, ds is a number. And you know what a dot product of two things is. This means we can write df, okay, as let's say the magnitude of the gradient of f times the magnitude of t, but that's just 1. Okay, and then we have a cosine of the angle between them, and then we've got ds. Okay, so this theta is the angle between the gradient of f and t. Okay. Right. df by ds, okay, equals the gradient of f cosine theta. So the rate of change of our function as we move along the curve, okay, so we're standing on the mountain and we move in a specified direction. And the change in our function, in this case the height, okay, will be the gradient of f magnitude cosine theta. Okay, and theta is the angle between the gradient of f and the direction that we're moving. Right, so what does this gradient of f mean? So this is maximum when cosine theta is 1. Okay, remember cosine theta goes from -1 to 1. Okay, and it's 1 when theta is 0. Okay, so when theta equals 0, this means that the gradient of f, which is a vector, is parallel to the vector t. Okay, because theta is the angle between the gradient of f and t. Okay, so this is maximum. So the rate of change of your function is maximum when the gradient of f is parallel to t. Okay, so the gradient of f is a vector. It's a vector in the direction of the maximum increase of your function. Okay? It's the steepest way up your mountain. Okay, so you look around on the mountain and you look at the steepest way up. Okay? Okay, so it's the direction of the fastest change in f. Okay, and it's minimum when cosine theta is -1. Okay, and that's when the gradient of f and the tangent, okay, the direction you're moving, are antiparallel. Okay, so that's straight down. That's the steepest way down. Okay. All right, let me tidy this up. Okay, so we saw that the change in the function along a path, so let's say df by ds, we saw that it equaled the gradient of f dotted to the dot product with the tangent vector. Okay, and this gradient is the direction in which the function changes fastest, and this tangent vector is the direction in which you're actually changing. You're following. Okay, so there's some curve with a tangent vector t, okay, which may be different from the direction of this gradient vector. Okay, so maybe the gradient vector is in this direction. Okay, and I'm writing this now as a partial derivative just to keep consistent with what we saw before for the derivatives df by dx and df by dy and df by dz. Okay, so if we say that the tangent vector t is in the direction of x, so this is just the unit vector in the direction of x. Okay, so it's the vector 1, 0, 0. Then what does this mean df by ds is? Df by ds is equal to the gradient of f. What's the gradient of f? It's df by dx, df by dy, df by dz. Vector dotted with the tangent vector. And in this case, the tangent vector is just 1, 0, 0. Okay, so if we take the dot product of this with this, then we get df by dx times 1, and then we get df by dy times 0 plus df by dz times 0. So the answer is that df by ds in this case is equal to df by dx. Okay, as we expect it should be, because we've chosen to move in the x direction. Okay, so we should regain our old result, okay, which we do. Okay, and so this is kind of why we use this partial notation. So this is the directional derivative. Okay, and you get the same thing for y and z. So if the tangent vector t is along z, so unit vector k, or we can write it as 0, 0, 1. Okay, then in this case, it's this dotted with 0, 0, 1. So df by ds is just equal to df by dz. Okay, as expected. Okay. Okay, so let's make it a bit clearer about the directions that we were talking about. So let's think about a function of two variables, z equals f of x and y. Okay, so this is a surface. So let's draw the x, y, and z axes. Okay, we've got x and y. Okay, and the value of the function is z. Okay, and maybe the surface looks like this. Okay, in 3 dimensions. Okay, so maybe we're thinking about the shape of a mountain. Okay, so the x and y are just coordinates and Z is the height of the mountain at any XY coordinate. Okay, now you can draw what are called contour lines. Okay, and these are lines of constant Z. Okay, so these are contour lines. Okay, and they are lines of constant Z. Okay, so each of these lines represents a different value of Z. Okay, so maybe it is the height of a mountain. This line may be Z equals 10 meters high. This is 15 meters. Okay, it's not a very high mountain. This may be 20 meters. This 30 meters. Okay, and we'll have maybe 0 at the bottom. So this is the ground. Okay, 5 meters, 10 meters. Okay, so if you stand anywhere on this line, okay, you will be 5 meters above ground level. If you stand anywhere on this line, so this part of the mountain, okay, you will be 15 meters above ground level. Okay, so if we stand on top of the z-axis and look down, then what do we see? We see x and y. Then these contour lines are closed curves in this plane. Okay, so maybe our ground level is this one. Okay. Zero meters. So any value of x and y that lies on this curve is you standing at ground level. Okay, then 5 meters up is any point on maybe this line. Okay, that's 5 meters up. So again, we're looking down along Z. Okay, so we've flown on a helicopter above our mountain and we're looking directly down on the peak. Okay, and then, so this is 0, this is 5, maybe 10 meters. Looks like this. Okay. Maybe 15 meters is like this. And then 20 meters. Okay, 25 meters. And say 30 meters. Okay. And eventually we get to our peak. So, what is this gradient vector? So we said that this gradient vector, okay, the gradient of f, or grad f, or sometimes this is also called del f, okay? Some people call this symbol the del symbol, del. This vector, it's a vector, so grad f is a vector in the direction in which the function has its greatest rate of change. Okay, and the direction we're talking about is a direction in x and y. i.e. we're standing on the mountain and we look around, we're choosing kind of the points on the compass. Okay, it's in the xy plane. We hold the compass in front of us. This is an xy plane. And we're choosing the direction in which to walk. Okay, if we walk, we will go up and down the mountain. Okay, but the direction we choose is in the x and y plane. Okay, and that's this plane that we've drawn. So the gradient of f is a vector in the direction in which f changes fastest. And that's at any point in this domain. So if you are here, okay, you're standing at the ground and you're asking what direction does f change fastest? Well, it's going to be straight up this way towards the peak of the mountain. Okay, if you're here, the direction in which f changes fastest is towards the peak of the mountain. Okay, it's not this direction, because that just takes you around the base of the mountain. Okay, along this line you're just standing on the ground at the base of the mountain. Okay, and maybe at this point, okay, where is the fastest increase? It's maybe not pointing towards the peak, but maybe it's up this way. Okay, and if we see contours getting close together, then that indicates a fast change in the height of the mountain too. Okay, so if you're here, then the fastest change is in this direction. Okay, and the rate of change is going to be large. Okay, so the magnitude of the gradient here is going to be large. Okay, so the curve that we were talking about before, when we had this and we drew the little tangent dr, which was t ds. Okay, the tangent, or this dr, is in this xy plane. Okay, so we're thinking about a curve that maybe goes through the xy plane. All right. So we're thinking about what happened when we move along this curve. Okay, and tangents to this curve. Okay. Okay, so this curve is defined in the xy plane. Okay, we don't need z to define this curve. So the gradient of f is the direction in which the function changes fastest. Okay, but maybe we don't want to go the steepest way up the mountain. Okay, maybe we're lazy and we want to take a meandering path. So maybe we start off at the ground, okay, and we want to go this way around the mountain, okay, to the top. Okay, so we want to ask the question, what is the rate of change of the height of the mountain? So what's the rate of change of f as we go around this curve? Okay, so the rate of change of f around a curve we saw was given by df by ds, and this is the gradient of f magnitude cosine theta. Okay, where theta is the angle between the tangent on the curve. So let's say at this point, okay, our tangent's this way. Okay, so theta is the angle between the tangent and the gradient, and at this point the gradient of the curve is like this. Okay, and you see here that the tangent and the gradient are almost perpendicular. Okay, so cosine theta will be close to 0, so the function will hardly change. And this is what we see, because as we're walking around here, we're walking around the contour basically, okay, which is a line of constant z. Okay, so we're choosing a very lazy path where we're barely going up and down the mountain.